and they were done by Brian May. So.
We all know who that is. Guitarist of Queen.
Yeah, but I wonder who. I wonder if the graduate students actually know that. Yeah, I've got some.
Get more people.
Okay. Take the whole thing.
Here we go.
There are only 3 images, but they're cool. So. I want these back. Thank you.
So it's 3:30, so we're going to go ahead. If people come late, they suffer, right?
Yeah, absolutely.
It's an enormous pleasure to welcome Hal Levison, who is a longtime member of our Boulder community. I'll tell you, notice I'm not reading from any notes here. This is from memory, in part because what Hal does is kind of emblazoned in my memory. The colloquium that you gave, maybe it was 25 years ago, or
Probably was 25 years ago.
or 30 years ago, was one of the most memorable colloquia I've ever heard, and I can still tell you what it was about and all the rest of it. But let me give you a little bit of background. Hal got his PhD during the Great Bombardment, which is quite a long time ago, something like that. And then he joined SWRI in Antonio, Texas in 1992. And then along with Alan Stern was one of the 2 people who founded SWRI Boulder, which if you go downtown, you can find it. It's still there, right?
We actually, now they allow us to have a sign on our building. So.
And they didn't used to?
No.
Right.
It's legal in Boulder to put signs on your building.
And Hal told me SWRI is now 130 people from 2 to... what are the rest of us doing with the rate of growth of our community? So,
and let me just say, if I can interrupt.
Yes.
Okay, so a lot of that has to do with a CU alumni, Robin Knupp, who is now, we hired her as a postdoc, and she's now our boss, right? And a lot of the growth happened because of her.
Are you still hiring?
Always.
Always. Okay. So this is where graduate students, where are all the graduates? Oh, they're here. Some of them can get jobs. Anyway, a little bit more.
You have to like rocks.
Just to prove that I do remember what you talked about. You talked about solar systems and the arrangement of planets and small bodies in the solar system. And that was a subject that back in the day I was really interested in, and you solved that problem for me. And you also showed me how you can make presentations without using, I can't remember the name of it, but anyway.
Unfortunately, NASA made me start working in PowerPoint, so.
If you're interested in talking with Hal at any time, he's kind of available and local, right?
Yeah.
So you can email him and say, tell me more about your stuff. He is PI on a grand new mission, which is going to fly very shortly.
Well, it's flying.
It's flying, okay. Yeah. It's on its way.
I'll
Lucy.
show you data.
And, okay, I'll shut up now. Hal.
Yeah, the only thing that I will add to that is, because some of you will know him, is my thesis advisor was Doug Richstone, and my dissertation was on the orbit of stars and galaxies. So I've evolved quite significantly. And I'm going to talk to you about Lucy, which is a discovery mission from NASA that launched in 2021. I'm going to show you some pictures of the launch. It launched at 5 in the morning, 5:30 in the morning. And even the people who lived in Kennedy said it was one of the most spectacular launches they've ever seen. I'll show you some pictures, but I encourage you all to go and look on the web. It was spectacular. The plan is to visit, which we've done the first two, is visit main belt asteroids as rehearsals for our spacecraft. There were two, one in 2023 and one in 2025, and I'll show you some results from them because they turned, at least one of them turned out to be an amazingly interesting object. Then we're having 5 Trojan encounters from 2027 to 2033 for a total so far of 8 objects. We've studied our targets pretty extensively from the ground, and we've discovered, or from the Earth, I should say, and we discovered 2 satellites, one with HST, which is why I said from the Earth rather than the ground, and the other with occultation. So we have 2 satellites, but we also have, and I must admit, you're not supposed to love one of your children more than the other, right? But my favorite of our targets is this near equal mass binary called Patroclus, which is at the end of the mission. So I have to stay alive until 2033. But before I start, I'm going to just sort of make the argument of why small bodies are interesting in the solar system. Now, you heard, right, my approach to science, I'm a theorist, right? Lucy is the first mission I've ever been associated with, period. Before that, I did large-scale simulations of planet formation and the evolution of the solar system, trying to understand how the solar system came to be, right? So to me, the money shot is this plot, right? What you see here is the eccentricity of an orbit versus semi-major axis. That's a log plot. The size of the dot scales with the mass of the object, and you can clearly see the 4 inner planets. Let me see. All right, Mercury, Venus, Earth, Mars, and Jupiter, Saturn, Uranus, and Neptune. So they're the 4 planets. I should point out that these are only objects on stable orbits in the solar system. But in addition to these, the planets are these small bodies, right? These objects are remnants of the formation of the planets, right? But unlike the planets, which have their own internal processes going on, and they've been bubbling and doing all these kind of things internally, the small bodies have basically been frozen in time since the formation of the solar system. So from my perspective, and this is true when I was a theorist too, right, rather than just a babysitter, right, from my perspective, if you want to understand the history of the solar system, you need to go and understand how these small body reservoirs came to be. So we call them the fossils of planet formation, and indeed we named the Lucy mission after the Lucy fossil, right, to make the connection that we're trying to learn about our origins. I should also point out this is our logo. The Lucy fossil was named after the Beatles song Lucy in the Sky with Diamonds, right? So we weren't sure if NASA was going to be happy trying to make the connection with that. So we hid it. Turns out they're fine with it, but we hid it by making our logo diamond-shaped. So, you know, the planetary community has understood the importance of these populations for a very long time, and you can see that in the fact that they sent a lot of spacecraft to study these small bodies. These are only the spacecraft that actually, their main targets were small bodies. And the way to look at this is, as I said before, these are only objects that are stable, but a lot of these objects become unstable. So for example, let's look at stardust. If you want to understand, stardust studied a comet that was on that orbit, but it was unstable, and it likely came from the Kuiper belt, so it's out there. So the dotted line indicates the location of where they formed. And as you can see, all the small body reservoirs that we care about have been studied, but one, right? And that's the Trojan swarms right in here. And that's what Lucy's going to do, and it's going to do it in spades, right? Because we're visiting a lot of objects. So let me talk about Trojans for a little bit and why they're interesting. First of all, as I said, I'm a theorist, right? So I'm going to go in and I'm going to say, well, this may mean that pebble accretion is right, or this may mean the Nice model is right, and stuff like that when we go through the interpretation of these things. So I always put this first bullet up here to remind me to tell you that this is a mission of exploration, right? We're going to a population that's never been seen before. And because of its proximity to the orbit of Jupiter, it's not supplying any meteorites to the Earth either. So of all the small body reservoirs in the solar system, this is the one we know least about, right? Because we can't go and pick up a piece of it at all. Now, when we started studying these things from the ground, people were surprised because we expected, due to the fact that they fit into a really small region of orbital space, we expected them basically to be all the same in the leftovers of the accretion of the core of Jupiter. And so people were really surprised to find they were not a homogeneous population, that they were very different from one another. And there's several ways to look at this. I'm going to just concentrate on two in this talk. The main one being these, what we call spectral types, were basically just the colors, right? Where C objects are gray, D objects are red. This goes from 4,500 angstroms out to 2.5 microns in these plots to give you an idea, and here are the slopes, right? So, and these are sort of halfway in between, and the Trojans are made up of about 50% Ds, 50% Cs, 50% Ps with a little bit of Cs mixed in, right? About 7% of the population is C types. And that's going to become important in the story we're going to tell in a couple minutes. Another way to look at this is to look at albedos. This is a WISE, it's a near-infrared albedo. This is a visible albedo. And this is the distribution of the known albedos. And you can see it goes, let's take the visible, go 13% albedo, which is really dark. This table is probably about 13% albedo, to 3% albedo, which is really, 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 really dark, right? So I think, right, getting back to the talk, you remember, right, that what we're seeing is objects that formed in different regions of the solar system got mixed together during an instability of the giant planets, right, and got trapped in the Trojans, right? This is something, one version of this is called the Nice model. In the Nice model, we start off with Jupiter and Saturn, in this case, Neptune and Uranus, all within 12, 13 AU of the sun. Remember, Neptune's out here at 30 AU. Now, if you put this in the computer, and I'll show you this in a minute, and integrate their orbits, you find that it can be stable for a long period of time, but eventually the solar system goes unstable. The ice giants get scattered out of the disk, and the dynamical friction between the planets and the small bodies circularize the orbits of the planets, leading them to the orbits that we see today. This disk is now totally gone, except there's some of it in the Kuiper belt. But if you look at it, we find that the probability of these objects getting trapped in the Trojan swarms is independent of where they form, because they basically get mixed up really quickly, right? And as a result, we're seeing, if this model is right, we're seeing a mixture of all the material that formed in the protoplanetary disk, which is now gone. So if you want to understand the protoplanetary disk, I would argue the Trojans are probably the best place to go look at it. So let me just show you an animation of that. So you can see the there's four giant planets in this disk of material. Now, when we were originally trying to explain the impact record of the moon and a long-lived tail to the impacts. So you can see 300 million years into this, and this thing is stable. Don't blink. Right. So you might be asking yourself, why would you believe such a crazy idea, right? And believe me, 90% of the field said that when we first suggested it. And that is because it explains a lot. First of all, it allows Uranus and Neptune to form, right? The standard picture of planets forming from planetesimals, this is work I did with Glenn Stewart, actually, a long time ago, right? We showed that you cannot get Uranus and Neptune to form in the standard picture in their current locations. Because once Jupiter and Saturn are formed, when Uranus and Neptune start to grow, once their escape velocity becomes comparable to their orbital velocity around the sun, they're more likely to hand things off to Jupiter and Saturn, which kicks them out of the solar system, than they are to recruit them. So once they get to 3, 4 Earth masses, they just stop, right? So this allows Uranus and Neptune to form. It explains the orbits. This is an old calculation of the giant planets. We get the irregular satellites of the giant planets form. And to me, one of the most interesting things is this is the Kuiper belt. This is semi-major axis and eccentricity. It's got this very complicated structure, and our models do a good job of explaining that as well. It also explains the Nice model, the Trojans. Oh, hitting the wrong thing. The orbits of the Trojans. By the way, the Trojans were what convinced me that this might actually be right, okay? Because all the models of Trojan formation before the Nice model had the Trojans forming when there was a lot of nebular gas around. Nebular gas damps inclinations and eccentricities. So although you could make Trojans during that time, they all had 0 inclinations and 0 eccentricities, and that's not what we see. And the community spent a lot of time trying to figure out how you can excite inclinations and eccentricities in the Trojans without losing them. No one came up with a good answer. What we found is that we can just capture them in their excited orbits during this process. So this is what convinced me that we might actually be right. And we still might actually be right. But having said that, subsequent work on our original model had a problem, right? And that is we destroyed the Earth. Now, you know, I'm a good theorist, right? I'm always skeptical of observations, right? But I couldn't quite convince myself that the Earth wasn't here. So, but it turns out you can save it by adding a 5th planet to the system, right? So what you're seeing here is a plot. This is by work by David Nesvorny. This is semi-major axis as a function of time. And there are 3 plots for each planet. One is semi-major axis, one is perihelion distance, one is aphelion distance. So here's Jupiter and Saturn and the 3 ice giants. And you can see the system goes unstable. This guy gets ejected, moving Saturn out and Jupiter in a little bit. And it's the fact that Jupiter moves in discrete jumps because it's interacting with the ice giant that actually ends up saving the Earth. So, and this turns out this model with 3 ice giants does a better job of all the observations that I showed you that the Nice model can explain. Right? So we published the Nice model in 2005. If you would have told me we still would be talking about it in 2026, I would have said you're absolutely crazy. You never know when you have an idea that can be long-lasting. But the interesting thing about this, is getting back to the Trojans, is as I said, the stuff trapped in the Trojan swarms represent the entire disk, right? So we can learn about that disk and the conditions that existed in this region of the solar system. But the only way, by studying the Trojans, but the only way we can do that is to understand the diversity. I should have said when I was talking about these different colors, we don't know why they're red, right? We don't know what causes the color. differences. But you can easily imagine color changing through this disk because the temperatures are changing in the disk, right? So to try to understand what the physics of that is, right, we can study this population, but to really understand it, we need to understand what the diversity means, which means going to a lot of objects, and that's exactly what Lucy is designed to do. So I'm going to talk about the trajectory. I'm a dynamicist. I love this, right? This was a work of art, right, that was done by a guy by the name of Brian Sutter at Lockheed Martin when we were putting the mission together, right? We are going to more objects in orbit around the sun than any other spacecraft in history. So let me just show you this, because I think it's beautiful. So this shows a launch date of October 17th. It was actually October 16th. We launched on Atlas V 401, which is the smallest rocket that we could use. We were trying to save money in order to do that, right? As a result, our velocity with respect to the Earth was actually quite small. So the first thing we did is launched in an orbit with that had the same semi-major axis as the Earth, but was slightly more eccentric. Then we used a series of Earth gravity assists to kick the spacecraft to higher and higher semi-major axes so it can get to the Trojans. This, I missed this. This flew by right above Australia, and it was first magnitude. So people went out and actually watched Lucy go by, waved high. So then we were in an orbit with an orbital period of 2 years. Right after perihelion in that, we flew by our first of our rehearsals, which I'll talk a little bit about this before, which we named Dinkinesh. I should point out most of these objects were not named. We got to name most of them. So, and I'll tell you a little bit about that. I'm showing you an artist's conception here of Dinkinesh. It's actually Bennu, right? But we now have data, so I can actually show you what that looks like. And it was an amazing object. We fell back into the inner part of the solar system, had a second Earth gravity assist, which kicks us out of Trojan swarms. On the way through the asteroid belt, we passed an asteroid we named Donald Johanson. By the way, we're about here now. Enter the leading swarm of the Trojans, right, where we're going to have 4 encounters. The first is with Euripides and its asteroid that we discovered with HST, Keta. A few days later, this is going to be tough, is Palomelli and its satellite, Sean. Go through Aphelion, come back in, go through past Lucas, Oris, fall back into the inner part of the solar system. We're going to use an interesting dynamical trick that if you put an object with a perihelion near the Earth and an aphelion near Jupiter, its orbital period is roughly half the orbital period of the Trojan. So on the first orbit, we can go through the L4 swarm, have another Earth gravity assist to target our final object, which is this really cool near equal mass binary called Patroclus, right? And notice the asymmetry there, right? That's because Patroclus is high inclination, and we chose to go there rather than hitting a large number of less interesting Trojans, right, in the L5 swarm. Okay, I talk about diversity. I've already showed you this plot. This is visible albedo, this near-infrared albedo. The gray dots represent the diversity of the Trojans, and here are our targets. We're covering that diversity. This is an artist's conception of our targets. We've got 2 Cs, 1, 2, 3, 4 Ps, and 2 Ds, so we're covering the spectral types. But I have to say, you know, I like to say I've been studying at the feet of the celestial mechanics gods for 40 years, right? And they are paying us back. One of the things NASA wants to see when you submit a proposal to them is the timeliness. Why do they want to do this now? Right? It turns out the trajectory I just showed you is highly unusual. So we did the experiment for the proposal where we asked ourselves, what happens if we launch in 2030? Right? And it turns out we could get maybe 2 or 3. None of the objects were particularly interesting, right? This is really a special trajectory, not only because we're getting this diversity, but the objects that we're going to study are worth sending spacecraft to, even if it was the only place the spacecraft were going. And I'm going to talk about 3 of them. The first is this Euripides and its satellite. Euripides is the largest member of really the only disruptive family collisional family in the Trojan swarms. Here's inclination, here's eccentricity, here's the L4 swarm. You see this grouping here. This was once a single object that was collisionally disruptive, and the fragments went off into space, but the velocity of the ejection is low compared to the orbital velocity around the sun. So when you look at these things in orbital element space, you see clumps, right? And Euripides is the brightest. I have to say, we've been having a lot of debate of how to pronounce these things, right? And I used to call it everybody's, but we had a classic professor come and give us a talk on how we should be pronouncing these things, and I was wrong. It's Euripides, so there you go. So I may slip every once in a while and call things 2 things. Euripides is right in there. Remember, the planets that we see really formed by 2 processes. The first is the dynamics as things are orbiting around the sun, and the second is the accretion when 2 things hit. So it's collisions and it's dynamics. That's what makes the planets, right? These families are collisional byproducts, right? And so they should be interesting and constraining when it comes to the growth of the planets. We've never visited an object like this before, and so that'll be interesting. But what's more is that there's this weird thing going on. Remember I said that the Trojans are about half P's and half D's with a little bit of C's. These are the gray objects mixed in, 7%. Most of Euripides is a C-type, right? So you may ask yourself, well, wait, what's the chance of the rarest object forming the only family? And then you realize that most of that 7% are part of that family. So C's are really rare in the Trojan swarms, right? And yet the biggest family is all C. That's telling us something, I think, fundamental. I think what's going on is that whatever makes these things red is only skin deep, right? And inside, all the Trojans are C-type objects. And when you break them open, you turn the red thing into a gray thing, right? And so that's what I think is going on here. If that's true, when we get to our red objects, young craters should be gray. So we're making a prediction about what we should see. Also, we discovered using HST a satellite that we named Keta, right? It is a teeny thing, about 1 kilometer in diameter, right? And that's consistent with the collision 2, because that same simulation I showed you before, when you look deep inside, you find that several of the fragments ended up in orbit around the primary after the collision. So it should be interesting too, being a fragment of a disruptive collision. Now I'm going to talk about my favorite, Patroclus and Menecius. This is a nearly equal mass binary, right? You can see their sizes. I shouldn't be pointing to my screen. You can see they're almost exactly the same size. Another way to see this is an HST observation of it. They're not resolved in HST, but you notice they're the exact same brightness, right? So that gives you an indication of the same size. They're about 100 kilometers objects on a nearly circular orbit, about 700 kilometers apart, right? And this kind of binary is really weird and unusual in the inner part of the solar system. Now, what I mean by that, in this case, is the inner part of the solar system means inside the orbit of Neptune, where planet formation occurs. It turns out that if you look at a region of the Kuiper Belt called the cold classical Kuiper Belt, which is beyond the reach of the planets, almost all of them are these near equal mass binaries. Something like 50%, and there's a lot of observational bias. They are all over the place, and you can see some pictures, including this was a object that New Horizons flew by. It's almost an equal mass binary. So what I think this is telling us is this is the least perturbed, dynamically perturbed location in the solar system, right? You're seeing the most primitive things. And when you look at the most primitive things, they're all, or almost all of them, are binary. And that, I think 20 years ago when I got in this field, would have blown everybody's mind. But it turns out that the best theories for the formation of planetesimals, small objects like this, are now predicting that. So let me take a minute and talk to you about that, starting off with going back to the standard picture of planet formation. In standard picture of planet formation, you have dust, right? The dust comes together and sticks and grows, right? And you start with dust, you end up with pebbles, and then you go to boulders, then you go to mountains, you go to cities, you go to planets, right? That's basically the story. And that works on the two ends, right? On the small end, little dust grains, and if you go to my house and look under my bed, you can see this happening. It's the experiment that I'm running, right? Small dust particles will come together and stick due to electrostatic forces, and things will grow. If you get bigger than, let's say, a kilometer, two things come together and will stick because of gravity. But if you're in this range, electrostatic forces are too small and gravity is too small. This is called the meter barrier. This has been something people have been aware of for 30 years. You can't get things this size to grow in the standard accretion picture of how planets form. Okay, there's actually 3 reasons that you can't get them to grow, but that's the one I think is easiest to understand. So people have been trying to understand this for a long time, and then Yoden and Goodman, now a long time ago, but now people are believing it, came up with this idea of a streaming instability which couples the dynamics of things that are about this size, meter size, something like that, right, with aerodynamic forces. And what they find, and I'm going to show you a movie that David Nesvorny and his collaborators did. This is a moving box in the solar nebula. There's gas in this, but you don't see the gas. What you see is just the pebbles, and the color of the pebbles indicate the local density, right? And what you see is you get a radial instability, making these things form into thin rings, and then they collapse to form basically little star clusters, right? Which evolve in this nebula, right? You can see them evolving. Now, this particular calculation can't resolve the clumps, right? So, but if you put all this into an n-body calculation, which they also did, this is what happens. So this is a lot like a binary star. There's enough angular momentum in these clouds that you can't fit all the material in the one object. And so the natural evolution is you end up with 2 objects that are the same size, right? So the streaming instability actually predicted what we see in the Kuiper Belt. And if that's true, then almost all the earliest macroscopic objects, remember, these pebbles are supposed to represent things this size. Those clumps are 100 kilometers. So we go basically from objects this size to 100 kilometers. By the way, that's an orbital period. So it happens like that, right? In the Kuiper Belt, it'd be 300 years. At Jupiter's orbit, it'll be 10 years, right? You get these macroscopic, huge objects of 100 kilometers in size. And they're almost all binaries. So what's going on in the inner part of the solar system is dynamically, these are very fragile objects. And so the growth of the planets is so violent that they don't survive, which is why you see them in the cold classical Kuiper Belt, but not anywhere else. except occasionally. So if that's true, right, what Patroclus represents is a rare leftover from that original planetesimal population. That's why it's my favorite. Let me talk about Polymele and Sean. We didn't know anything about this object when we made, including the existence of Sean. And by the way, it's in quotes because we don't have an orbit for it yet, so it's its nickname, right? We knew almost nothing about it except it was small. But because it was small, Lucy has this automatic tracking software to make sure that the instruments stay on the target as we're flying by. And we were worried that an object as small as we thought this was wouldn't work, right? So one thing we wanted to do is really understand its size, and we studied it with stellar occultations and found something really interesting. First of all, we found it had a satellite, okay, which we named, well, the nickname of the people who discovered it is Sean, after Sean the sheep, right? I won't go into why they decided to do that, but it was a misunderstanding of what Polymele meant, okay? But we got some 6 or 7 occultations of this thing, and we're able to put together a shape, okay? And the shape is basically a hamburger. It's an oblate spheroid with almost a 3-to-1 axis ratio. And that blew our minds. Particularly, is everybody would have said before this object was discovered, is that if you look at objects this size, and you can see it's about 20 kilometers in effective radius, right? If you look at an object, it should be a fragment of a collision in our understanding of the evolution of these small bodies. But for the life of me, I can't think how you can preserve that shape during a collisional cascade. But if you go back and now look at the streaming instability objects, what you find, and this is another simulation of theirs, looking at it from almost edge on, is you get these disks. These disks go unstable, they generate spiral arms, and coming off the end of these spiral arms are these very flat hamburger-shaped things, right? So if this is true, Polymele is also a primordial object. Right? So we're going to go see 2 of them with Lucy. That's, to me, very exciting. So let's go back to the diversity. I'm not going to talk about some of these things. We've covering all the known spectral types. We're going to the L4 and the L5 swarm. We're looking at a remnant of a disruptive collision. We have a near equal mass primordial binary. We have this really weird flattened oblate spheroid, and Lufkus, I'm not going to show this, is an ultra slow rotator. It's got a rotation period of 550 hours, right? Which no one can understand. We also have diversity when it comes to sizes, right? For example, Polymele is 160 times smaller than Patroclus, and also we have different collisional histories, right? As I'm arguing, Polymele and the binary hasn't changed much over the history of the solar system, but everybody's was probably twice as large when it formed. Then we are adding, just to show you the entire target list, I've added the main belt asteroids here too. So let me just talk about Lucy, right? Remember, diversity is the key. To cover the diversity, we have to be moving really fast, right, to get to the objects that we see, right? So this is just flybys, where we're not stopping, we're not sniffing, we're going by between 6 and 9 kilometers a second. So we're really moving, right? To put this in perspective, Lucy's mission is 12 years, and all our important science is going to be collected in 24 hours. The rest of the time is just going between the objects, okay? But we're going to do everything we possibly can with a flyby. We're going to look at surface geology. We're measuring colors and compositions. We're going to get masses and shapes, gives us density, so we'll be able to tell you something about their interiors. And of course, we're looking for satellites and rings. We're doing this with this, if you don't mind me saying, spectacularly beautiful spacecraft, even though it looks like Mickey Mouse, right? So to put this to scale, our high gain antenna right here is 2 meters. Lucy is 50 feet from wingtip to wingtip. We're going further from the sun than any solar-powered spacecraft in history. Maybe this will help you put it to scale. And on top of the spacecraft is this articulating platform, which has 4 or 5 instruments on it, depending on how you want to count. Okay, we have basically a panchromatic telescope. This is a high-resolution camera. We have 2 panchromatic low-resolution cameras. This is not really part of the science instrumentation, right? But it's in order to keep the spacecraft pointing at the target as we go by. But it turns out it's going to be critical for us to understand the shapes to get the density. We have a thermal infrared spectrograph supplied to us by ASU. I should say Lori is supplied to us by APL. And then we have this instrument called LaRalph, which is 2 instruments in one. It's a color camera and imaging near-infrared spectrograph. It's really going to be the workhorse, I think, when it comes to composition. We go everywhere from about 5,000 angstroms all the way out to 50 microns when we're observing this. I should point out that TESS is a single channel instrument, so we'll just be getting the spectra out of that. I'm going to show you some eye candy, right? So this is we call this platform the instrument pointing platform. Here it is down at Lockheed. The spacecraft was built at Lockheed Martin in South Denver. Matter of fact, this is almost an entirely Colorado mission, right? The science team and the science operations and everything is in Boulder. The spacecraft was built and is being flown at Lockheed in South Denver. And we even used ULA, which is also in South Denver, as a launch vehicle. So it's almost entirely Colorado. I learned something when I gave a talk to some press people a few months ago. Did you know that aerospace was the 2nd largest industry in the state? Right? So that's pretty cool, right? After, after tourism. This is the spacecraft on the shaking table, right? We wanted to make sure the most dangerous part of this, the whole process is launch. It's feeling something like 30 Gs. So we put the spacecraft on this big panel of this big platform and shook the hell out of it. So that's what you're seeing it here. It passed even the first time. One of the cool things about the spacecraft are solar arrays. They're cloth, and I'll show you a picture of them in a minute. And this is them folded up. All folded up, they're 4 inches thick, or they were 4 inches thick. So there they are, one unfolded. They're so large that Lockheed Martin didn't have a clean room where you could open up both of them at the same time. So we had to open one, fold it back up, and then flip the spacecraft upside down and backwards, and then open the other one. All this is to support it because it's not meant to be in 1G, right? The dark areas of the solar cells and what you see as copper is actually Kevlar cloth, right? So this is the spacecraft down at the Cape before we put it into fairing, right? Here's a picture of a bunch of us. Like, can you tell which one was me? This is a beautiful picture taken of it before it was in the fairing. This is the spacecraft going off to the launch pad. This is at the launch pad. This is me and my family, my wife, my 2 daughters, and some guy who just won't go away.
A little noisy, but I'm so excited. Lucy is going back in the sky with diamonds. Johnny will love that. Anyway, if you meet anyone up there, Lucy, give them peace and love from me. And NASA, peace and love. Don't forget, my name is Ringo. Peace and love.
Like he had to tell us. And you notice it's sort of tacked on at the end, right? I thought that was cool. He came in and gave a concert last year here, and I got to meet him, which was fun. And that's the launch picture video. And a launch picture, I have to say, go find the video. It's gorgeous because there was this bank of clouds, and the spacecraft disappears into the clouds and then erupts, like Fingers of God, Close Encounter of the Third Kind type of thing. It was really gorgeous. For most people, I was actually too close. So for me, I just disappeared in the cloud and I never saw it again. But if you were out where the plebes were, you really got a nice show. Okay, so let me talk about some of the data that we took. The first object we encountered was this object. It was on November 1st, 2023. It's an object called Dinkinesh. This was not in our original plan, but one of our team members looked at our trajectory and just asked themselves if we got close to an object or not that we could go visit. It turns out we got within 64,000 kilometers of this. The chances of that is like 0. It's a fifth of the wave between here and the moon, right? So we could get there and have the encounter with it with almost no delta V, right? Fuel is a key commodity on Lucy, and we use it to test this autonomous system, keeping the target in the field of view. Here's basically what we knew about it before the encounter. It was unnamed, so we decided to name it Dinkinesh, which is the name of the Lucy fossil in Ethiopian. Right? So that's how we came up with the name. But it turns out to be scientifically interesting for several reasons. First of all, it looked nothing like what we expected it to look like. But it also is sort of a missing link, which is sort of fitting for an asteroid named after the Lucy fossil. Because when we look at the asteroids we've studied in the main asteroid belt, they're all really big, right? Except for Dactyl, which is the moon of Ida. They're all many kilometers in size, right? If you look at the asteroids we studied, part of the near-Earth asteroid population, it's about the same size as that. So it's sort of the missing link between these two populations. Our estimate was about 700 meters in diameter, which turned out to be right. I'm just showing you the geometry. This happened after the spacecraft reached aphelion, so it was heading back towards the sun. So we're coming in from the dark side and heading in. I just wanted to show you this so you could understand and see the geometry when I show you the movie, The Encounter. That was our first image. Now, carefully look at that. And this is what we thought.
What the hell is that?
Right? Look at it. Right? It's got this thing sticking out. Well, it turns out when we got additional data, and that literally was the first image. What's the chance, right, that the first image down is the one that had the satellite sitting right behind the object? But it turns out there's a satellite, which is pretty cool. But that's not really the shocking thing. And believe me, we were shocked. Let me show you the movie. So you can see the satellite. Look at it. Something's weird's going on. It's a contact binary. No one's ever seen anything like that before. It really blew our minds. We drank a lot that night. So this is the first contact. Now they're contact binaries known to be just in orbit around the sun, right? But this is the first satellite that's a contact binary. that anybody's ever seen. And the interesting thing, I think, something that really needs to be explained, and we don't have a good explanation for it, is these two lobes are almost exactly the same size. So that's telling us something really fundamental about how these satellites form, although I'm not sure what. So we named the satellite Salam, right? Salam is a fossil of a human ancestor that's the same species as Lucy. It's older by a few 100,000 years, but it died when it was about 3 years old. So people were calling it the baby of Lucy, so we figured that would be a good name for a satellite of Dinkinesh. This thing is really small, right? So that's Salam, that's Dinkinesh, that's the Eiffel Tower, the Empire State Building, and my deputy PI is Italian. Okay, so let me tell you a little bit about this, because this blew our mind, because we actually had light curves from the ground for this object, and when we interpreted it, we interpreted it to be totally different than what we saw, right? So this thing is an oblate spheroid. It's almost a sphere, right? It's, you know, 2 axes, about 400 meters. The short axis is about 350. The 2 lobes are about 100 meters in size, right? Volume ratio is about 17:1. We've been able to determine that, and this is not surprising due to the physics, that Salam is synchronously locked around around Dinkinesh, so it looks sort of like that. The semi-major axis is about 3.1 kilometers. Dinkinesh is a fast rotator. This is a plot of rotational period versus diameter for, I think there are 10,000 asteroids on this. This line represents the place where an object is, if it's a rubble pile, spinning so fast that it'll fly apart, which is why you see a pretty sharp line here. Dinkinesh is down here. So it's about 90% of its breakup speed. And I think that is important to its history. And in order to do that, let me explain to you something that we call YORP. So if you take a satellite, an asteroid, whatever, and put it in the sun, it heats up. And when it radiates the thermal radiation away, right, asymmetries on the shape of the object can lead to torques on the body. And so they speed up or slow down, right, depending on just the bumps and wiggles on the surface. Right, for example, if you look at this, this was drawn with a triangle on one side and a flat edge on the other. You can easily imagine most of the angular momentum of the photons are going off of 45 degrees here and parallel the equator here, so you get a spin up, right? And the interesting thing about objects that are about the size of this object is this becomes important on timescales of only a few tens of millions of years. So unlike many asteroids, something that's 20 kilometers, nothing's happened. Remember I said that early on. For these objects, they are moving and shaking their entire history, right? As they speed up and slow down and mass moves around and things like that, changing the shapes so the torques change. It's really complicated for an object this size. And in particular, it can lead to satellite formation. Imagine this object is slowly spinning up, material sloughs to the equator, and as it continues to spin up, gets launched into orbit, and you end up with a satellite. That's how we think the satellite formed. The interesting thing about the contact binary is how that formed. You can imagine 2 events forming 2 satellites that came together, right, after they were in orbit, but why are they the same size, right? That's something I think still needs to be answered. Put on your glasses. This thing has a really interesting, I think the red goes on the right, but maybe you're all right because you're all doing it the other way. Just let you stare at that for a minute. So the geology of this object is really, really interesting. Okay. So let me talk about it. First of all, we see an equatorial ridge. That's not too surprising, right? Because if the satellite formed the way I said it did, with material sloughing over the equator, you would expect an equatorial ridge to form at the same time. And it goes, as far as we can see, all the way around Dinkinesh. But it also has this trough, which is not something we would have expected to see, right? That again goes almost all the way around the body. And we think what we're seeing is fracturing, right? Due to extensional failure. So I played this game. That's the real image of just taking this chunk and moving it in. You can see it looks almost axisymmetric when you do that. So I think what you're seeing is something like Africa and South America, right? That two pieces that were together, and as it spun up, it sort of broke apart, right? That increased the moment of inertia, decreased the spin rate, and the thing slowed down. That's why it's near critical spin up, right? Because this thing fractured and moved apart. The interesting thing about this is this implies that there's some strength to this body, right? So we're still trying to understand what that means. The satellite is really weird too. It also has a ridge, at least I think it does. It's one of our biggest arguments. Yeah, you put on the, you can see it. I mean, look at the ridge. It's one of the biggest arguments we have at beers after our science team meeting is whether this thing is a ridge or something else. I think it looks like a duckbill, right? It doesn't extend all the way around the body, but it's certainly in the area that's facing Dinkinesh. We have no clue what this means yet. Also, look at that. It's tilted. It's not in the equatorial plane, right? I think that happened, well, right? This thing's going to settle in where it's rotating around the shortest moment of inertia. So when the two guys came together, right, I think it shifted the moment of inertia, and that's why the whole thing sort of rotated when it came together. A lot of fun stuff to do here. I really do think it looks like a duckbill. Okay, let me talk about Donald Johanson. We had that encounter.
Think about ending up soon, so we have time
Oh,
for questions.
sure. Yeah, I don't have a lot to say with this. This was sort of like we thought. It's interesting. It's part of a collisional family in the asteroid belt that's only 130 million years old. So it's one of the youngest objects we've ever visited with the spacecraft. So we know it was about 5 kilometers. It was named after Donald Johanson, the discoverer of the Lucy fossil. He actually came to the encounter. So that was pretty cool. I think it's the first time somebody whose asteroid was named after them was actually at the encounter with the spacecraft, right? So he was there, and I don't know if you recognize that guy. He was there. That's Brian May of Queen. You know, he's got a PhD in astronomy. In case you didn't know that, and he did all the stereo imaging I showed you, right? So he's a member of our team. That's pretty cool. Here's a movie. Small movie. There you go. Now we had to stop the taking data before we got to close encounter because we wanted to avoid the spacecraft rotating the instruments into the sun if it went into safe mode during the encounter. So we shut it off early. That's our best image, right? It sort of looks pretty typical, except for the neck. The neck actually turns out to be strange. That's the size of these things, right? The neck is smooth and axisymmetric. For those of you who know me, you won't be surprised. To me, it looks like a stacked of beer pints, something that looks like that, right? And you can see the ridges, right, representing the edge of this. I always think of beer pints, right? But you can see these nice, well-defined ridges on this body that, again, we don't really understand yet. Another interesting thing about it is the neck. The neck looks really smooth, right, compared to the rest of the body. But if you look at the size frequency distribution of the craters, they're the same. But if you look at the craters in detail, the ones on the neck are sort of morphed and deformed while the ones in the rest of the body are not. But that deformation didn't remove any craters because even the small ones we see. So that's sort of a process that we don't quite understand yet. Okay, so where are we? This is about where we are today. We're heading out into the L4 swarm. We have our first Trojan encounter in April 2027. It's really getting close. 35 days later, we have another one, right? So one of the things that we have to do is we're doing all the science sequences now. So everything will be done by the time we get there. And then we can just have fun looking at the data. So I will stop. Thank you. By the way, if you want to learn more about Lucy, here's a QR code to our website. So anybody interested can copy that down.
Just a little time for questions. Go ahead.
Simulations of the evolution of the big system. How much do you have to assume about the interior structure of
Nothing.
Jupiter?
Everything is just point masses. That simulation, well, what I said isn't quite true. Dynamically, they're just point masses. We put in the physical size so that we can get accretion, right? But besides that, it's just, there's a sphere around all the bodies, and it's just gym m over r squared, basically, right?
Huh.
Done a little bit fancier than that, but yeah, right. It's symplectic, so that it's a little fancier than
that. All your instruments look really great for exploration. Did you promise NASA some binary test of the Nice model that there will be a clincher observation one way or the other? Just going to
No,
go
that's
out
a
there and
losing-
say, what
that's
the
a
hell is that?
Yeah. No, I mean, we talked, that's a losing proposition in a proposal, I think. Right? You never want to say, this or that or something like that, right? The word that was quite common in a proposal was inform or constrain. But really the reason to do this is we don't know what these things are, right? And the fact that it's going to tell us constrain the origin of the solar system, I think, or the evolution of the solar system is, I think, to them, secondary.
Two more questions.
You show a slide where you had the asteroids from the Lagrange point 4, 2 from the Lagrange point 5. There was a big difference in their sizes. Is there a reason why these difference?
They just so happen to be the ones we could get to, right? Again, I talked about this idea that beholden to the celestial mechanics gods. We originally tried to plan this so that we'd go to 2 objects, right? And everything else just came around by luck, including going to the L5. So the guy who designed this had to, one of the things NASA requires is that we don't hit anything for 50 years, right? So the guy who was designing the trajectory just put a bunch of objects in and made a movie. He put my asteroid, he put his asteroid, right? And he put a couple famous of the Trojans in, and he integrated past the end of mission. And we're watching this thing, and it goes around, and it goes right by Patroclus. And I was like, oh, can we go there? And he said, probably not, it's high inclination, and we're seeing projection effect, it's really not getting close. But it turns out it's just crossing the plane of the ecliptic at the time the spacecraft is going by, right? What luck is that, right? Like I said, it's celestial mechanics gods. They're looking after us.
So thanks for the talk, Hal. It's going to be a great mission. I want to double down on Nick's question, which is about if or how we can constrain dynamical models like the Nice model or 4 ice giants versus 5 ice giants in the early solar system.
Well,
You said
fairy tale I
constrained and
tell myself-
informed. Are there things that we can measure in the solar system today?
The hope is the near-infrared spectrograph on the instruments will give us ideas about organics on the surface, right? If we can use the colors to understand where in the solar system it formed, then we can use the distribution of the spectral classification and the mixing ratio of different types to constrain how the instability occurred. That's the story I tell. Now, let me just say, it's not going to work, right? But that's a story I tell myself. And remember, if you look at every mission in history, the important things is what we didn't expect. So I'm going to talk about, I can make a story, and I did with NASA, right? You know, it's bullshit. It's quality bullshit, but it's bullshit, right? When you write these proposals, right? And we might be able to do that, right? But it's really, we're going to see something we never expected, events or something that tells us really fundamental history about these objects.
I think we should. I know
Thank
there
you.
are more questions. Please come down and ask now. You want your red and blue?
Yeah, I want my glasses back, please.
You want my glasses?